Hello dear students. In today's class, let us learn about the theory of compound pendulum. I hope that you are already familiar with the basic physics of simple pendulum. In a simple pendulum, you have a point mass that is suspended from a point called the point of suspension, and the system is made to oscillate. So you can find the equation of motion of the system and you can evaluate the equation to find out the necessary details of the system like the time period, angular frequency, the basic pattern that the system will follow, the trajectory of the system and so on. Similar to that, in the case of a compound pendulum, let us try to understand its basic physics. So as we all know, a compound pendulum has a distributed mass and it is not like a simple pendulum where we have in fact a point mass. So this is the distributed mass that we have, and this is suspended from one particular point, like maybe an axis that is passing through this point, and this point is called the point of suspension. And we know any distribution of mass will definitely have one point called the center of gravity, which is the balancing point of all the gravitational force that is acting on this body. So this one particular point can be thought to be the point where all the gravitational force is acting upon. So this point is similar to the concept of center of mass. Center of mass is that point where all the mass of the system seems to be concentrated. If the gravitational field is uniform, then the center of mass and the center of gravity are same because the gravitational force acting on all the points are the same and the center of gravity will be same as center of mass. So as for now, center of gravity is that point where the gravitational force is thought to be concentrated, is thought to be acting upon the system. So these are the two specific points inside this compound pendulum. The compound pendulum is fixed at this point, at the point of suspension, and it is oscillating like this. So if this system as shown in this figure is in its equilibrium position. So if you leave the system like this, it will continue to remain stationary like this because there is this gravitational force that is acting at the center of gravity, and this point of suspension actually keeps this body fixed here by acting up a counter force, a normal force that balances the system. Now let us try to understand what will happen if we try to apply a small displacement, if we try to give a small displacement to the system. So suppose I displace this compound pendulum slightly to the right side as shown in this figure. So as we all know, the body will now be displaced by say an angle theta from the equilibrium position. And now let us try to find out the total torque that will be acting upon the system. So earlier, as we have seen, there were two forces that were exactly cancelling out each other. But in this case, when this body is displaced slightly by an angle theta, there is a net torque that is acting on the system. So let us try to calculate that. Now we know even when the body is displaced by an angle theta, the gravitational force will be continuously acting downwards in the downward direction. Its magnitude is given by mass into g, where m is the mass of this body and g is the acceleration due to gravity. Now this force is acting at the point of center of gravity, but the body is fixed at the point of center of suspension or the point of suspension. And between these two, there is a distance of L. We say this L as the length of the compound pendulum, which is defined as the distance between the point of suspension and the center of gravity. Here, this particular length represents the length of the compound pendulum. It is not the physical length of the pendulum, It is the distance between the center of suspension and the center of gravity. Now this force acting at the point of center of gravity is the root cause of a torque. So as we all know, torque is the rotational analog of force, and you can write the equation for torque as tau equal to R cross F. Now what are these R and F? So if this is the point, suppose this is the axis of rotation as we define in the case of a rotational motion, and this is some perpendicular bar fixed here, and you are applying a force like, say, like this. Now this point is fixed, this is the axis of rotation, and this bar can move, and we say that this is the vector R. Now in order to calculate the total torque that is acting on the system, you translate this force vector to this point of suspension here. And then you calculate the angle theta between the force and the R. After that, calculate R cross F to find out the torque acting on the system. So we know R cross F is given by RF sin theta. So that is the total torque acting on the system in this particular case. Similar to that, we can evaluate the torque acting on the system. So I must say that the torque acting on the compound pendulum can be calculated in a variety of ways. You can also find the opposing force that is acting at this point of suspension, and then you can split these two forces into different components, find out which all components cancel out, and then find out the other component, and so on. That is one way to do it. So let us stick to this equation tau equal to R cross F in order to evaluate the total torque acting on the system. So here, as we know, what is the force acting on the system? It is the mg force acting in this direction. And here the vector R is defined as the vector from the center of suspension until the center of gravity. Here the magnitude of R, which is the total length from the point of suspension until the center of gravity, is L. So I can write magnitude of vector R is L here, and the magnitude of the force vector is mg. Now what is the angle between this force and this R? To find that, we have to move this force vector to the point of suspension, and in this case, this is the point of suspension and mg is the force acting downwards. I have just translated the vector towards this part. As we all know, we can actually translate the vector without changing its direction and its magnitude. And here the angle between R and F is given by this value theta. So what is the total torque acting on the system? Total torque, tau will be equal to R is L, then F is mg multiplied by sin theta. So this is the total torque acting on the compound pendulum. Now since this torque is a restoring torque that actually tries to bring this compound pendulum back into the equilibrium position, we should add a negative sign to this equation. This negative sign actually implies the restoring nature of the torque, just like the restoring force. Now let us try to remember the basic fundamental equation for torque. We know torque can be defined as I alpha, just like we define force equal to ma. The rotational analog of torque is I, the moment of inertia, multiplied by the angular acceleration. So change force to torque, change mass to moment of inertia, and change acceleration to angular acceleration alpha. So just like we write ma equal to m into d square x by dt square, we can write in the case of torque, this is equal to I into d square theta by dt square. So we have two equations for torque. This equation applies to the case of a compound pendulum. This is the total torque acting on a compound pendulum. And this is the general equation for torque. And comparing 1 and 2, we can write the equation for the compound pendulum as I into d square theta by dt square is equal to minus mgl sine theta. Now this is the equation for a compound pendulum, the differential equation corresponding to the compound pendulum, which can be rewritten as d square theta by dt square is equal to minus mgl divided by I sine theta. Now this is the general differential equation corresponding to the motion of a compound pendulum, or we could say the equation of motion could be obtained from this. This is the differential equation corresponding to the motion of the compound pendulum. So if you analyze this particular equation, you could actually obtain a lot of values that are relevant to the system. Now this equation is very similar to the equation of oscillation, the general equation of simple harmonic motion. Now let us write that. In the case of angular motion, it is given by d square theta by dt square equal to minus omega square theta. So here we have a sine theta factor here. As we know, when angle theta is very small, if theta is small, sine theta can be approximated as theta itself. So under this particular condition, this differential equation can be rewritten as d square theta by dt square is equal to minus mgl divided by I into theta. So these equations are one and same when theta is small. Now the general equation for the simple harmonic motion and the equation that we have obtained for a compound pendulum are quite similar. So if we compare these two equations, we can find that a compound pendulum also undergoes a simple harmonic motion, since d square theta by dt square is proportional to negative of theta. The basic features of a simple harmonic motion is satisfied by a compound pendulum. So we can say that a compound pendulum executes simple harmonic motion. That is evident from this differential equation. d square theta by dt square is proportional to minus theta. That implies that compound pendulum executes simple harmonic motion. Now we could also compare this differential equation with the general equation of a SHM, of a simple harmonic motion. So if we compare these two, we can identify that omega square and mgl by I are same. In the case of compound pendulum, this mgl by I, this term actually stands for omega square. So I can write omega square is equal to mgl by I in the case of a compound pendulum. Or equivalently, omega is equal to root of mgl by I. Now we know the angular frequency and time period are related as time period is equal to 2 pi by omega. So this is equal to 2 pi divided by root of mgl divided by I, which is equal to 2 pi into root of I by mgl. So this is the equation for time period. So we were able to extract the time period of the system just from the differential equation of motion of the compound pendulum. So that is how this equation becomes useful in evaluating various properties of the system. We got the angular frequency, we could find the time period, and if you solve this differential equation, you could find the equation for theta, which will yield you the position of the compound pendulum at various time. You could also find the angular velocity and various other parameters from this single equation. That is the relevance of this differential equation. So we have got the equation for time period of the system. Now what are the various terms here? Here I stands for the moment of inertia of the system with the axis passing through the point of suspension. So if this is the axis and if this system is made to rotate, what is the moment of inertia? That is the term I. And the other terms are M stands for the total mass, G is the acceleration due to gravity, and L, as we have already seen, is the distance between the point of suspension and the center of gravity, which is defined as the length of the compound pendulum. Now, one of the vague parameters in this equation is the I term, which is the moment of inertia of the body when the axis passes through the point of suspension. Axis through point of suspension. Now, since the point of suspension is arbitrary, you can fix the point of suspension at any particular point in the compound pendulum. Let us try to redefine this moment of inertia in terms of some of the known terms of the system. For that, we turn into the parallel axis theorem from the rotational mechanics. So suppose we know the moment of inertia of the system about the axis passing through the center of gravity. So this is center of gravity, and if an axis is passing through there, it is easy to find the moment of inertia of such bodies. So if there is any symmetry for this body, you could actually easily evaluate the moment of inertia of the body when the axis passes through the center of gravity. So suppose we know the value I0 corresponding to the moment of inertia of the body when the center of mass is when the axis of rotation passes through the center of gravity. Now, in order to find the moment of inertia corresponding to the present case, from the parallel axis theorem, I equal to I0 plus mass of the system multiplied by the distance between the two axes square. So in this particular case, the parallel axis theorem will be like this. So this is the axis for which the moment of inertia is I. This I is to be evaluated. We already know the moment of inertia I0 corresponding to the axis passing through the center of gravity, which is defined as I0. The distance between these two axes is given by L, and the mass of the system is M. Then the parallel axis theorem is given by I equal to I0 plus M into L square. So applying that equation, we can find I equal to I0 plus ML square. Now again, instead of I0, we can substitute I0 equal to mk square, which is the basic definition of the moment of inertia and the radius of gyration. Here k is the radius of gyration. So this is a basic definition for any body. We actually define the radius of gyration as that critical value for which the mk square will give you the I0. So if you happen to know the radius of gyration, you can easily find I0. So the radius of gyration is that distance at which the whole mass can be concentrated. Suppose this is the distance k, and if it is made to rotate around the center of gravity, that will have the same moment of inertia. So in terms of this radius of gyration, we can easily define the moment of inertia about the center of gravity. So since I0 is equal to mk square, we can rewrite the equation for I, which is I0 plus ml square as mk square plus ml square, which is equal to m into k square plus l square. Now substituting this back into the equation number 3, we can obtain T is equal to 2 pi into root of m into k square plus l square divided by mgl. So m will cancel out, and the remaining terms can be written as 2 pi into root of k square by L plus L square by L, which is L itself, divided by G. So this is the equation for time period of a compound pendulum. L is the length of the compound pendulum that is defined in a specific way. K is the radius of gyration of the compound pendulum, and G is the acceleration due to gravity. Now let us compare this equation with the equation of a simple pendulum, which is T is equal to 2 pi into root of L by G. Here L is the length of the simple pendulum, which is the length between the point of suspension and the point where the mass is situated, or the center of gravity of the system. Now we can see that when this L is equal to this term k square by L plus L, these two equations are one and same. So often this term k square by L plus L is defined as the length of the equivalent simple pendulum. So if you want to construct a simple pendulum with the same time period as the corresponding compound pendulum, as the present compound pendulum, then tie this mass at a length of k square by L plus L from the point of suspension. So if you keep that length as k square by L plus L, then you will have a simple pendulum of same time period. So that is another important concept that you can remember. Also, you can define one another point inside the compound pendulum, which is the center of oscillation. So as we have seen, L is the distance from the center of suspension until the center of gravity, and from there take another length k square by L and fix a point there. So as you can see, this is the total length capital L. L plus k square by L is the length of the equivalent simple pendulum. So this particular point is often referred to as the center of oscillation. And we can actually prove that the center of oscillation and center of suspension are reversible, meaning that if you keep the center of oscillation as the suspension point, even then the system will have the same time period. In that case, the center of suspension will act like the center of oscillation. So you can try to remember that concept too. As for now, I hope that the basic concept is clear for you. The theory of compound pendulum, the derivation of the differential equation, and the analysis of the differential equation to find the time period is clear for you. Thank you.